when are two vector spaces isomorphic? So let's say we have two vector spaces over the same field, two vector spaces over F. These are going to be isomorphic if they have the same dimension. But even better than that, if and only if. This goes in both directions. So two vector spaces over our field are isomorphic if they have the same dimension, and if they have the same dimension, then they are isomorphic. Okay, so a lot to prove. It's an if and only if. I want to go in both directions. Proof. Well, first, let's suppose V and W are isomorphic. Then there's an isomorphism. Or I'll say let phi be the, I'll just say let instead of then. Let phi from V to W be the isomorphism between them. Okay, so now we have the isomorphism. And what do I want to show? Well, I want to show that they have the same dimension. And what do I know? I know that the dimension of V equals the dimension of the null space of phi plus the dimension of the range of phi. Okay, so now I know that phi is an isomorphism. So that means phi is a bijection. So that means it's injective, and the only thing it sends to 0 is 0. So what's the dimension of the null space? Well, the whole null space is just 0. So this is equal to the dimension of the range of phi. But the range of phi is contained inside W. Okay? So the dimension of V equals the dimension, well, that's a waste of writing, but which is inside W. But what else do I know? I know that it must, well, the dimension isn't inside W, the range is inside W. Okay, that's better. So, what do I know about this range? Well, I know the range has to be all of W because it's surjective. So, the dimension of V has to be the dimension of W. So first of all, I get rid of this because of injectivity, and I get this, which is equal to this because of surjectivity. The range must be everything. So this was a waste, and that was a waste. I could have went right to that, but I didn't. Okay, other direction. Now we will suppose that the dimension of V equals the dimension of W. And I want to show that there's an isomorphism between them. Okay, so what do I know? Well, let's say V has basis of V1, V2 through Vn, and W has basis W1, W2 through Wn. Okay, and by the way, all of this is finite dimensional, otherwise none of this would have made sense. We couldn't have even been talking about dimension or whether or not they had the same dimension to begin with. We should keep that in mind. Okay, so say V has this basis and say W has this basis. Okay, what do we want to show? Well, we want to show there's an isomorphism, so we're going to have to define a map. Okay, so how am I going to define a map? Well, I want to define a map from V to W, and here's how I'm going to define it. I'm going to say phi of alpha 1 V1 plus dot 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 through alpha n Vn is equal to, well, I'm going to make it easy. I'm just going to switch the v's with w's. Now we have the same field. We said that, 2 vector spaces over f, so we don't have any different fields, so this is a perfectly fine map. Okay, and well, you might say, okay, how come this is a good way to make, how does this define phi, right? Well, what do I know? I know that v1 through vn is a basis, so that means every single element of v can be written in this way, and every single element can only be written in one way. So there's no confusion as to where this takes any element. For any element of v, we can only write this in one way, and if I put it inside phi, what do? I just switch the v's to w's, and I get this. I could have also done this by saying what phi does to v1 through vn and so on, whichever. Okay, so what do we want to show? Well, we want to show that this phi is an isomorphism. So let's think about it. What is it injective and is it surjective? So let's think about that. I mean, is it surjective first? Well, any element of w can be written in this form, and we have the element right here that goes to it, so it's definitely got to be surjective. Is it injective? Well, the only way I could have two things going to the same element would be if I somehow had two things going to the same set of coefficients over here. But the only way to get the same set of coefficients over here is if I had the same set of coefficients over there. So this is going to be injective and surjective. And no, I did not write out those arguments. I could write them out, but you could also write them out because I just told you where they were. That might not be a horrible exercise to do here. I'll say it one more time. Every single element in W can be written in this form, and this shows you what goes to it. So it is surjective. And it is injective because if I had two things going to the same place, that means I have two things going to the same set of coefficients over here. And the only way I could get that would be if I had the same set of coefficients over here. And one more time, I'm using heavily the fact that we have bases here, because otherwise I could write the same thing on the right using different coefficients. I can't. Each element only has one set of possible coefficients, and because of that, the only way I can get to that one set of coefficients is if I have the matching coefficients over there. Okay. One more thing. Why is phi linear? We know it's injective, we know it's surjective. Why is phi linear? Well, this definition is the same definition as if I said phi of vi equals wi. Because if phi of vi is wi, then phi of alpha 1 v1 through alpha n vn would equal this simply by the linearity of the map. So if I define my phi using this rule, and then I just extend linearly, I get this, and I know that any linear transformation is completely determined by where it sends its basis elements, and I know that any possible mapping of basis elements determines a linear transformation. So that says that this is linear. So I have phi is injective, surjective. I didn't write much, but I've covered everything in my words here. And it is also linear. So one more time, for the linearity, this definition is the same as saying phi of vi equals wi. This determines a linear map, because any assignment of basis elements to basis elements determines a linear map. And what linear map does it determine? Well, by linearity, by the rules of linear maps, we get that phi of this would equal this as well. So, what have we concluded? We've concluded that if we have isomorphic vector spaces, they have the same dimension. And if we have vector spaces with the same dimension, then they are isomorphic. So both of those things. So powerful stuff, goes in both directions, and that's the proof.